Hey, what is up, honors chemistry students? And today we start Unit 10. The title of Unit 10 will be the gas laws, and we'll start with 10A, which is called pressure and Dalton's law of partial pressure. So we'll learn about some of the scientists involved in discovering what pressure is, and then we'll talk about our good friend John Dalton that we've learned about him already and what he gave to the concept of studying gases. Remember, gases, we've talked about already in terms of the KMT, the kinetic molecular theory, and the assumptions of the KMT, like particles are elastic. We talked about diffusion, expansion, compressibility, how far apart the particles are, all those things. Now we get into some math involved in gases. So, what is pressure? Here is the definition: force per unit area on a surface. So, force over an area. Force over an area. Right now, I want you to take your index finger and press down on something that's near you. Maybe it's your computer. When you press your finger on your computer, you are creating a pressure. So, there's a force moving through the tip of your finger onto the surface of your computer. The SI unit for force is the Newton, which is just abbreviated with a capital N. We will not really use that. It's just an FYI. In reality, it's a kilogram times a meter over a square second. So a very unique unit for force. The overall equation for pressure is force divided by area. And again, that's more of an FYI. We really will not use that equation in this unit. We'll use other equations involving pressure. I wanted to show you some things involving pressure. And I want to start with my dogs. I have two Boston Terriers, Pixie and Ruby. Pixie is 10, Ruby is 4. And they're small dogs. Pixie weighs about 10 pounds and Ruby weighs about 20 pounds. But I will tell you, every time they jump up on top of me when I'm on the couch watching some TV, their paws dig into my body. And we can really explain that in terms of pressure. They have small paws. So, because they have small paws, the pressure of their body is over a small area, or the weight of their body is over a small area. So, there's a high pressure on my body. If they had huge paws, I would not be as uncomfortable when they jumped on top of me. You may have seen stuff like this. People, the bed of nails, right? Circus acts and other magicians have used this trick forever in the hopes that you, the viewer, would think that all of those nails would go through the person's body. And the reason that it does not, those nails do not go through a person's body, is because of pressure over an area. Because there are so many nails and there's such a big area, the pressure is dispersed amongst every nail such that it does not harm this individual. If I took all of those nails away and left one there, what do you think would happen? Just one nail. Yeah, you guessed it. All of the pressure from this man standing on that one nail would be driven through this man's body. Boxing, just another example. So, out of these gloves, the one on the left, very, very small gloves, versus the one on the right, very, very large gloves, which ones are more dangerous? And you can probably guess. The ones with the smaller surface area are the more dangerous ones. So the MMA gloves can deliver much more pressure with a punch than the large gloves on the right. I've actually boxed with the large gloves on the right, and it's very difficult to deliver any type of sustainable blow with the large gloves. Um, and even more dangerous would be somebody's fists without any gloves, because then you can really deliver a lot of pressure through, say, one or two knuckles. A little mathematical relationship: as surface area decreases, pressure increases, and vice versa. And that's kind of what we just talked about. The smaller the surface area, the higher the pressure, and the larger the surface area, the smaller the pressure. What type of mathematical relationship is that? Well, you've got two options. You've got indirect or direct. And we should know by now that if one goes up and the other one goes down, that is an indirect relationship, or you could also say it's an inverse mathematical relationship. Pressure depends on volume. So we know about volume. Pressure depends on temperature, and pressure depends on the number of particles. And those are things that we will talk about throughout this unit. What impact volume, temperature, and number of particles has on pressure? Who came up with pressure? Who figured this out? And obviously, it was Evangelista Torricelli, an Italian, who I'm not going to read this to you, but he was very much the first person to describe pressure in a mathematical way. And he used a device like this one on the right, where he used the liquid metal mercury, and noticed when he made this device that the mercury would go to a certain point, and that certain point was right around 760 millimeters of mercury, a definite measurement. And depending on the day, it might shift one way or the other, but it very much in his area of Italy stayed right around 760 millimeters of mercury. And this device is called a barometer. You may have heard of barometers. Barometers measure pressure, and especially used to measure air pressure, which is very relevant to our daily lives, because the pressure outside very much can tell us what type of weather we are having that day. Torricelli created it in the early 1600s, and I mean, if we were in class right now, I would make a barometer right in front of your eyes just using water. It's very easy to make a barometer. But Torricelli was the first person to come up with the concept. Pressure is unique in that there are so many different units of pressure, and I can't answer why that is. Like mass, we know is grams and kilograms, but pressure jumps around a little bit. So let me talk about some of the units. Millimeters of mercury, abbreviated mmHg, is what you will see a lot of the time. You'll see it on barometers. You'll see it on blood pressure takers, which are called sphygmomanometers. So a very common unit to measure pressure. Torr, T-O-R, you spell it out, is from Torricelli. It's a shortened form of Torricelli. And in reality, it's the exact same as millimeters of mercury. So if the pressure outside today is 760 millimeters of mercury, you could also say the pressure outside is 760 torr. Same thing. Atmospheres is another unit for pressure. With on Earth, we know at sea level that the pressure of Earth, of gas on Earth, is 1 atmosphere. So we'll see that in this unit. Pascal, abbreviated PA, another scientist who worked with pressure, is another unit, and it's the actual SI unit, and it's a Newton over a square meter. And we'll use pascals a little bit, and we'll use kilopascals also, which would be 1,000 pascals. The main conversion is right here. So, I already mentioned it. An atmosphere is the exact same thing as 760 milliliters of mercury, which is the exact same as 760 torr, which is the exact same as 1.01325 times 10 to the fifth pascals. And that is the conversion that you'll have to use to go between atmospheres and millimeters of mercury. You do not have to memorize that. It's on your it's on your reference sheet, or you can look it up. So just a little conversion practice. We're going to use the box method. We're going to get away from stoichiometry and go back to our box method. So I want to convert 0.927 atmospheres to millimeters of mercury. So I use that little conversion sentence, and that conversion sentence said there are 760 millimeters of mercury in one atmosphere. 760 millimeters of mercury in one atmosphere. So I'll start with what I know, 0.927, and then there is, I want atmospheres to cancel. And I apologize, I can't show you the box method very well on PowerPoint, so I had to go to the fraction method, which is the exact same. So I get atmospheres to cancel, and I put 760 millimeters of mercury in the numerator and 1 atmosphere in the denominator, and I would multiply those two, sig figs matter, to get 705 millimeters of mercury. If I want to convert it to torr, it's actually the exact same thing. So 0.927 times 760, 705 torr. Kilopascals, a little bit different in that there are 101.325 kilopascals in an atmosphere. So my final answer for kilopascals would be 93.9 kilopascals. Let's look at some more. 148.6 kilopascals converted to atmospheres. So we just kind of had one like this, but we're going the opposite way. There are 101.325 kilopascals in an atmosphere. So we want kilopascals to cancel out. This time I would divide to get 1.467 atmospheres. Millimeters of mercury. There are 760 millimeters of mercury in 101.325 kilopascals, according to our little conversion sentence. So I would have a final answer. For this one, I would have to take 148.6 times 760 and then divide by 101.325 to get a sig fig answer of 1115 millimeters of mercury. And just to show you that torr is the exact same thing, it's the same setup for torr and the same answer with a different end unit factor. So those are your conversions, just some examples, and we'll have some questions on the quiz involving conversions. Let's finish today with Dalton's law of partial pressures. And we know about John Dalton earlier this year. He was the guy responsible for giving us the atomic theory, which we went over in depth all the way back, I believe, in Unit 4. But Dalton did more than the atomic theory. He also studied the mixture of gases. And he said the pressure of a gas mixture is the sum of the individual pressures of each gas alone. So I want to show you a real-life example to help you understand Dalton's law of partial pressures. But before we do that, let me show you the equation. It's a very simple equation. It's addition, where PT stands for total pressure, and all you have to do is add up all the gases in a room or add up all the pressures of the gases in a closed-off beaker, and whatever you could when you add all those together, that will give you the total pressure of the room or the total pressure inside that beaker. So P1, P2, P3, P4, just depends on how many gases you have. That's why there's a dot, dot, dot. There can only be 2 gases, so that would be P1 plus P2. If there are 5 gases, that would be P1 plus P2 plus P3 plus P4 plus P5 to get your total pressure. So let's go to your house and what I think the pressure in your house is today as we speak. So we know that nitrogen makes up 78.09% of Earth's atmosphere. So the pressure of nitrogen in your room or in your house is 593 millimeters of mercury. Oxygen is second place. It makes up 20.95% of Earth's atmosphere. So there are 159 millimeters of mercury in your home right now of oxygen. Argon's in third place. Very small percentage of argon in your room, 7.07 millimeters of mercury. Carbon dioxide, even smaller, 0.304 millimeters of mercury. And then water changes every day, and that would go with this humidity thing we hear sometimes on from the weatherman or weatherwoman. So, how do I solve for the total pressure of your house right now? Well, it's very simple. According to Dalton's law of partial pressures, all I have to do is add all of those up, and that will give me the total pressure in your house. So I'm going to take my calculator out and just go 593, that's P1, plus 159, P2, plus 7.07, that's P3, plus 0.304, and the total pressure in your house, if we sig fig that, is 759 millimeters of mercury, which is exactly what we would expect it to be. Where at sea level, Earth is 760 millimeters of mercury. And here in Yorktown, Indiana, Muncie, Indiana, we are slightly above sea level, just slightly, which means there's not as much air sitting on top of us as there would be if we were in Miami, Florida, or New York City, or San Francisco right now on a beach. It would be 760 millimeters of mercury there. But since we're about 2 football fields above sea level, where you are in your home right now, we have slightly less air on top of us. So 59 millimeters of mercury, according to Dalton's law of partial pressures. All right. Just some more stuff about Dalton's law. The particles of each gas in a mixture have an equal chance to hit the wall. So this is the particle movement we talked about with the KMT, and how those gas particles are moving with high velocity, and they're bouncing off things. They're bouncing off you. They're bouncing off your head. They're bouncing off your bed. They're bouncing off your computer as we sit here and listen to this. Each gas exerts a pressure independent of that exerted by the other gases. So the nitrogen is independent of the oxygen, which is independent of the argon, and so on. But the total pressure is the result of the total number of collisions. So, picture-wise, blue would be one gas, red would be another gas. They have specific pressures by themselves that are different. When I put them together, all I have to do is add up those pressures, and that will give me the total pressures. So that top one would be P1. The middle one would be P2. Put them together would be P1 plus P2. Pretty simple. How do we use this in chemistry? We do it through water displacement experiments. So we want to figure out how much pressure is in a gas that is made during a chemical reaction, because if you remember, a lot of the gases that we produce in chemistry class escape into the atmosphere. If you remember, we added zinc to hydrochloric acid earlier this year, and hydrogen gas was created, but it escaped into the room, and then it's so light it escapes into the atmosphere, and a lot of it goes up and out of Earth. So scientists were like, how do we figure out how much gas is being produced? It's through a water displacement reaction. And you can see the setup here with potassium chlorate. You burn it, and you seal off the vessel, and you can see that oxygen is created from this experiment, and from using the water displacement method and Dalton's law of partial pressures, we can figure out exactly how much of that oxygen was produced. And we have to worry about some water vapor or water gas at the same time. So here it is. You take your total pressure, right? The total pressure is like what the pressure is that day. You can use a barometer, your PT. So we can assume it's like 760. And then your unknown is the P gas, the pressure of gas, and your known will be the pressure of water. So if you know the total pressure and you know the pressure of your water, all you have to do is subtract those two to find the total amount of oxygen, the P gas, pressure of the gas made in the experiment. So 760, and then we know the pressure of water. We can look that up on the internet. Depends, the temperature of the water plays a role in that. And then we're solving for the pressure of the gas, in this case, oxygen. So here's the little example, very similar to the one we just did, where we know I'm not going to read this to you, the barometric, all of it, the barometric pressure and the temperature during the experiment were 731 torr. So that's the PT, 731. And the water vapor, 17.5. So what's the pressure of oxygen collected? So that would be 731.0 is PT equals P gas plus 17.5. So to solve the problem, we would just go 731.0 minus 17.5 to get a final answer that the pressure of the oxygen was 713.5 torr. And that concludes 10A, pressure and Dalton's law of partial pressures. One last thing. Sorry, I forgot about this slide. Standard temperature and pressure is something STP used by scientists, used by more than scientists, really. Also used very much in the racing community, NASCAR and IndyCar. You'll see STP used a lot in those racing circuits. It basically stands for the standard pressure will be 1 atmosphere, and the standard temperature will be 0 degrees Celsius, which we should know is also 273 Kelvin. And so whenever you see STP, like I might say the environments in an STP situation, you should immediately correspond that to that's 1 atmosphere of air at 0 degrees Celsius. All right, and that officially concludes 10A. Have a good one, and I'll talk to you guys later.